Hello students, this video is designed to help you with the Unit 7 problem sets from lessons 1 through 5. I'm going to be looking at the problem sets from those lessons and giving you some helpful tips. As always, I'll show you the problem sets and I will let you try them on your own, and then you will unpause the video to see if you did them right. So take a few minutes to try to answer these questions and unpause the video when you're ready. Alright, take a look at these answers. One quick trick I wanted to show you is if it gives you coordinates, in this case it gives us these coordinates, and you are trying to find the length of something without using the distance formula, you can think of it as a right triangle. So from here we have 28 is our y value and negative 4 is our y value. That's a total distance of 32, so 32 on the up and down here. And then from our x values we go from 8 to 32. From 8 to 32 is a total distance of 24. So there's our right triangle. Well, you know that in a right triangle, the hypotenuse, the distance between the two ends of the legs, has to be greater than both of the legs. So 32, 24, the only correct answer here is 40. And if you use the Pythagorean theorem, you get the same thing. For this case, it gives us a scale factor of 2, which means we're multiplying things by 2. However, it tells us that it's centered at the point 0, 6. 0, 6 happens to be the y-intercept. If the center of dilation is on the line, that means that line doesn't change position. In other words, it's the same exact line. Alright, moving right along. This question asks us which linear equation could represent the image of a dilation. What we know about dilations is that they give us the same slope. So we can take this equation, even though it's not in standard form, and we can rearrange it so that it looks like one of these equations. In other words, I have a positive 3x here. I can subtract 4y from both sides to get 3x minus 4y, and I can move the number to the other side. If I have the two variables on one side and they have the exact same numbers, coefficients, and also signs, that means they're going to be parallel to each other. So 3x minus 4y, this can turn into 3x minus 4y. We'll see this again later on. This one, it tells us the dilation is by a scale factor of 6, and it also tells us that the dilation is centered at the midpoint of the segment, which means the segment doesn't move, the position doesn't change. The length of the image should just be the original distance times the scale factor. That should give us 18. In this case, there was a trick to it. You could have not used the trick, but the trick made it a lot faster. First of all, these say that it has a different slope, and as we know, it's always going to be the same slope for dilation, so we eliminated choices 2 and 4. This one says the same slope and the same y-intercept, and this one says same slope but a different y-intercept. It would have the same y-intercept if the point is on the line. So we're just going to test to see whether the origin is on this line. The easiest test to do that is to plug in or substitute 0, 0, which is the origin, into our equation. 3x minus 5y equals 4, 3 times 0, 5 times 0, 4. And you can see that 0, 0 is not a solution to the equation. The origin is not part of the line, which means that it's going to have the same exact slope, but a different y-intercept. It's going to be a different line. Dilated by a scale factor of 2, centered at a point not on the line segment, which means that the line is going to move. It's still going to be parallel, but it's going to move. So the line segments are parallels, correct, not perpendicular, which means right angles. And the image is twice the length of the given line segment? Well, that's true because we're dilating by a scale factor of 2, multiplying every number by 2. In this case, it asks us what the image is when we're dilating centering at the origin. It's the same type of question as the previous question. We're going to take this equation and rearrange it so that all the variables are on one side and then find the one that matches. It's simple as that. Question number 8, it tells us that the dilation is a scale factor of 2 and centered at 3, 8. Well, let's just test to see if 3, 8 is on the line. Well, you can see it right here. It's in big bold print. 8 equals 8 means that point is on this line. If the point is on the line, that means the exact same equation stays true. Remember, if the center of dilation is on the line, that means the line does not move. For question number 9, it tells us that the line is dilated by a scale factor of 3/2, and it's centered at the origin, which means all I'm going to do is keep the same exact slope, and I'm going to take the y-intercept, which is 0, -4, and dilate that. We went from 0, -4 to 0, -6 by multiplying -4 times 3/2. I trust you can do that by yourselves on your calculator. Anyway, this is the new y-intercept, and that goes here. Last but not least, I got a little crazy with my colors here. A line that passes through the points blah and blah It's dilated by a scale factor of 3 and centered at the origin. This was a very easy question. The answer to every single question talking about dilations is that it's always going to be parallel to the original line, always parallel. We could also know that since it's centered at the origin is not going to lie in the path of 1, 1 to 5, 7 because the slope between here and here is not 1. From 1 to 5 is a distance of 4. From 1 to 7 is the distance of 6. So the slope is 6 over 4 or 3 over 2. You can't go from 1, 1 down to the origin using that slope. All right, so that was the first part of the first page. Moving on to lesson 2 problem set. Again, you know the drill. Pause the video, try the problem set, and I will show you the answers in a moment. All right, these problems were fairly straightforward. I'm not going to walk you through each and every one of them. I do want to draw your attention to this. This is a quadratic equation. You must remember how to solve quadratic equations. Here's the next part. Again, well, this isn't quadratic. This is the Pythagorean theorem, but know how to solve equations that you learned about in algebra. And here is the last part. Mostly just proportions. Big over small equals big over small. All right, moving on. This is the problem set from lesson 3. We started looking at proofs. Pause the video and try to answer these sample proofs. Hopefully you got these proofs. They were very repetitive. This lesson was all about AA postulate, which means all we need to do is prove that two angles are congruent. In each of these cases, that's what we did. One angle, two angles. One angle, two angles. One angle, two angles. And the nice thing about this is, didn't matter which two angles we proved as long as they were two corresponding angles in the similar triangles. All right, moving on to the next page. Take a look at these, which were slightly longer proofs, and see if you can figure them out. Again, very straightforward proofs. I took the liberty of drawing some of the diagrams separately for you, but these proofs should be very easy to analyze. We're just looking for two angles to be congruent. Again, I redrew these two triangles to show you that they could be separated and also to show you that they're easier to name that way. All right, hopefully this makes sense. Onward and upward. Looking for lesson 4 problem set. Pause the video, try to answer these questions. Oh, by the way, real quick. On the previous page, this was a lesson 3 problem set. This said that STX is similar to VUT. This was a typo. You can go ahead and cross that off in your notes there. This should say VTU, not VUT. All right. Again, onward and upward, we're looking at the problem set for lesson 4. Pause the video, take a look and see if you can answer these questions, and then unpause the video and see if you did them right. If there's one lesson that I want you to pull out of these problem sets, it's draw the picture when you don't have it. In this case, you were able to draw the picture and you were able to say pretty clearly side, angle, side similarity. Very, very straightforward. Same thing here. We use the dots to represent proportional. For example, AC over DF. AC has one dot, DF has one dot. And then CB over FE, CB 2 dots, FE 2 dots. So the dots indicate similarity. Then we were able to use that SAS similarity to say, well, SAS means these two sides and the angle that's in the middle. So angle C and angle F. So angle C and angle F. Here, you should remember this. This was a problem from before, so get real. For number 4, you were able to do the drawings here and see that 0.3 repeating is equal to 0.3 repeating. These are proportional sides. Since they're similar, that means that these sides should be proportional. All the other sets of sides were not proportional. For example, 3 divided by 6, that's 1/2. 4 divided by 12 is 1/3, so that's wrong. For number 5, it gave you some information. Just label the diagram. If there was no triangles, you would draw the triangles, but since there are, you just label the diagram. And you're able to see pretty clearly that this is SAS similarity. 9 divided by 6 is equal to 15 divided by 10. So these two triangles are similar. Very straightforward. Second page of this same problem set. Pause the video, see if you can figure this out. All right, these proofs are slightly longer than the AA postulate proofs, but they're very similar in construction. We just need to prove that the two sets of sides are going to be proportional. We can do that by listing the numbers first, then by saying that they're proportional and saying what they are equal to. So in this case, they're both equal to 2 over 7, so we put that in, and we use substitution as our reason. Then we identify the angles between them to be congruent, and then we have SAS similarity postulate. Here was a little bit different. It asked us to explain why the triangles were similar. We knew that B and C were similar because of the fact that all of their sides are proportional. Same thing here. We noted that there was a similarity statement, which was SRT is similar to VUT. Oh, that's weird. My little line is going places. Here's where that line is supposed to be. Anyway, here's the proof. It's a very simple 5-step proof. One thing that you should remember is this right angle thing. If two angles are right angles as they are given in the diagram, then they're equal to each other, or I should say congruent to each other. All right, so this should have been it for lesson 4. Let's move on to lesson 5 problem set. Again, pause the video, try these problems, and I will give you the answers as soon as you are ready. In each of these problems, you could have used 2 different methods. You could have used the proportionality method, which you learned about during lessons 1 and 2. Proportionality means the small side over the big side is equal to the small side over the big side. That's what we used here. We also used proportionality here. Small divided by big is equal to small divided by big. We did that again here. Just keep in mind what it's asking for. In this case, it was asking for this piece down here, not the value of x, but the value of EC, which is going to be x minus 12. For this problem, we used something called the Side-Splitter Theorem, and side-splitter means something very simple. It means that, let me get my pens out here, it means that if I have 2 pieces involved in one of the sides of a triangle, and 2 pieces involved within another 2 sides of a triangle, and these 2 sides happen to be parallel, then we are able to say this: 4 divided by 6, the part that's next to the vertex divided by the part that's down by the base, is equal to x plus 2 over 4x minus 7, which is the part that's by the vertex divided by the part that's by the base. This is called the Side-Splitter Theorem. Again, we could have used the same thing that we used in problems 1 and 2. However, in this case, we would have to do 4 divided by 10 is equal to x plus 2 divided by, and then we'd have to add these 2 together. We'd have to add x plus 2 plus 4x minus 7, which is a hassle. So we solved for x, we got x is equal to 4, and then we answered what CE was by substituting that value into CE. For number 4, it was very similar. We did piece divided by piece equals piece divided by piece. That's a recurring theme in geometry, by the way. Piece divided by piece equals piece divided by piece. We're going to see that in the circles unit. And in number 5, it asks us for one of these weird perimeter questions. I highlighted the perimeter that we were talking about, the quadrilateral ABED, and I drew it over here. Listen, I can't stress this enough. If it doesn't give you a clear picture, redraw the picture to make it easier to see. Mine isn't super to scale, but it's much easier to see. All right, that was the first page of that problem set. Take a look at the last page of the problem set and pause the video, and then come back when you're done. All right, again, I use my invaluable tool of redrawing the diagram. Here we identified that I was looking for the length of EB. So if we're looking for the length of EB, that means we use x to denote that. And we also know that 3 and 6 together is going to be equal to 9, so we know the length of AD. So 3, 9, x, 15. We set up our proportion, we solved our proportion for x, and we found EB. For number 7, it was asking for which statement is false. It was looking for the one that didn't make any sense. And you can pick this apart and say, well, AC over AD. That's AC, the whole thing, divided by AD, which is this second largest piece, is equal to AB, which is this whole thing, divided by AG, which is this second largest piece. All of these made sense except for choice 3. You can see the diagram I made for choice 3. It makes no sense at all. Hopefully you're able to see that, and if not, you can redraw these triangles just the same way I did in the top one, and you should be able to see it. For question number 8, there were a number of different things you had to do, and some of them came out to be decimals. Hopefully you didn't get stressed out by that. Redraw the triangles. I keep saying it over and over again, but that's the easiest way to do it. And you can see my 3 proportions here. Try to follow those along and see if you did those correctly. And then finally, for question number 9, it was a real-world problem, which means it asks us to find things to the nearest measurement, in this case, the nearest yard. We set up a proportion. We got a crazy decimal, but our decimal ended up being 164.34 blah, 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 which rounds to 164. And this semi-equal to or sort of equal to, approximately equal to sign means I rounded somewhere. All right, this was the Unit 7 review for problem sets 1 through 5. Hopefully this was helpful to you. Good luck studying.